Notation. So here's the problem with this topic. And the problem is that there are so many different notations that represent the same thing. Now that's often can be a good thing, but often is also a very intimidating and overwhelming thing. Right? You look at this and you're like, okay, what's the point of all these different types of notations? And I think it's very overwhelming to look at it all just at once. It's much better to look at them where they naturally kind of occur, because certain types of notations are better than others. Like, for example, with fractions, right? Like sometimes you want things as an improper fraction, or sometimes you want them as a mixed numeral. They all have their kind of different purposes. And that's the same true for vectors. They all kind of pop up naturally where you'd expect them. Right? Let's have a look at this first. I mentioned that we can kind of think about vectors as coordinates. That was the computer scientist perspective, right? How does this kind of work? Well, if we think about this coordinate here, A, as x, y, it's like some point in the Cartesian plane, a vector, right, would just be the arrow that goes from the origin to that point there, right? And so that's how we can kind of think about this notation here. And this is kind of natural. If I'm using the vector, if I'm writing the vector O to A with an arrow on the top, is equal to xy, so we write that as a column. That's the vector from the origin to this point here. Did you guys do that in physics? Was that the kind of notation you used, or what did you guys use for that? When you drew the arrows out? Okay. Did you give the vector a name, or did you just kind of?
They gave value. They give us, well, they tell us, like, say if we had like a velocity, you'd be like from 60 degrees north. Okay,
right. Yeah. So you'd actually write that this vector is 60 degrees north and 5 meters. Yeah. Oh, they tell you. Okay.
We would draw the arrow at 60.
As an angle.
60 degrees and then like north to 60 degrees.
Okay, cool, right. So I guess in mathematics, again, like this is kind of like a perspective change, right? We're more interested in the vectors themselves, right? And so this type of vector, right, so this is why we give it xy, right? Because you've got a horizontal and a vertical component there. And this type of vector we call a position vector, right? Why do we call it a position vector? This is because it's from the origin. It's rooted at the origin. So anytime you have a vector that's rooted at the origin, we call it a position vector. And I suppose the name kind of implies why, right? Because it's literally relating to a specific position on the Cartesian plane. But if we kind of limit our vectors only rooted at the origin, it's not very interesting, right? We can't really go many places. So can we move them around? Well, yeah, of course we can, right? We can move them there. And then we can go, oh, I think I can put an animation for that. There we go, yeah. Just wanted to appreciate that. Yeah, I don't know, wait, too long for sure. That's okay, so these are our different vectors now. Now the question is, are these vectors, are they different? Or are they the same? I don't know. Do they look the same? Same magnitude? Yeah? Is the direction the same as well?
Depends on where you base it from.
So I guess the question is, so the magnitude I think we're pretty happy is the same, right? If you look at this, they look all the same length, right? But then how do we define the direction of a vector, right? Does moving it around the Cartesian plane change it at all? And I think the answer to that is that you go back to your first definition that you gave me, right? Vectors have magnitude and direction. So as long as the vectors have the same magnitude and direction, then they are the same. And in fact, when you look at these, right, how do you think about direction? You were talking about bearings, north 60 degrees east, right? If you kind of took this and you moved it back to the origin, that would have the exact same direction, right? So moving these around doesn't change the fact that these are the same vector, right? Obviously, it's in a different position now, okay? But it's still the same vector. It's still the same magnitude, still has the same direction. And these ones we call displacement vectors because we've kind of moved them around. Yeah. And I suppose one way we can think of it, because it can be anywhere now, it's a vector relative to where it was last. And in fact, they have the same horizontal and vertical components as well. Yeah. All right. And this is where we need a new notation, though, right? Because before, what did we have? We had O to A. Yeah. We can't do that anymore because, well, what does O represent? Generally, O represents the origin, right? So if O represents the origin, I can't use O to A notation anymore. So you'll see this notation a lot. It's it has usually it's a lowercase, and we'll have a little squiggle on the bottom. That's a tilde. Okay, so that's generally the notation that we use for these displacement vectors and for other vectors as well. Okay. So there's the tilde. our O to A notation, and our column notation. Okay. And yeah, this one also ordered pairs. They sometimes use that, but why do you think I'm not really a big fan of this? So I don't know why. You reckon? Yeah, it's a bit misleading because it can look like a coordinate at times. Yeah, so it's kind of like I'm a bit iffy about it, but just to be aware that it's something that you can see.